Hello. Thank you for organizing this event. I'm very excited to participate here, and above all, also thank you for inviting me to present this work. Really a big honor to talk about Nextflow here at Shanghai ABI. And also it's quite important event for this project, because we are celebrating 10 years since the first commit on Nextflow as an open source project. Project was started maybe in 2012, but was made open source 2013. So it's a good opportunity to say thank you to everybody involved into this community, everybody that commit code Nextflow, provide feedback, or just use every day like you are doing here. And so this is a very big opportunities again to say thank you, all of you. And also what I like to think sometimes about Nextflow, how this project managed to grow from a small idea originated into a small research lab Barcelona into something much bigger. And that is all. And then the main idea behind this project was to allow the scalability of data pipelines, remove all the friction that there is behind enabling the data pipeline. So, but also, above all, allowing scientists to focus on their work to allow collaboration. So these are the main idea behind this framework, and what we continue to work every day, that we continue to develop this technology. The point is that we are going forward, or we are going toward more complicated, more complex deployment scenario, which you want to use more cloud, you want to write more complex pipeline, you want to scale more your pipeline. So this is why we are evolving this technology from a single tool or single workflow engine to something more complex, to an ecosystem of technology in which there are different components, and which these components play a role to optimize the execution of the pipeline that you need to run and to deploy. So I'm going to talk today about a bit more about this technology, of course, about Nextflow, but also about Fuge and Wave, that are two new components that we are adding to this stack of technology. And the idea to start with this Fusion file system, and why we need a special file system for Nextflow data pipelines. Because the real challenge for the deployment of scalable pipeline in the cloud, but not only in the cloud, is the storage. It's not much the problem of computing. Computing is pretty easy to have. You can have just credit card by a lot of cloud computing resources, so it's not the limiting factor. But the point is how we can use computing in an efficient manner. To have efficient computing, we need an efficient way to manage data transfer into the deployment of our pipelines. Because at the end, these data pipelines ingest a lot of data, produce a lot of data, so it's key to have an efficient way to move data, efficient manner, optimal manner. So there are a lot of shard file systems, distributed file systems in the cloud, but most of the time they were designed for a different work. They were more designed for HPC. So they tend to be expensive. There are other services to be maintained. This is something that we would like not to have. Instead, the ideal solution when we deploy pipeline in the cloud is object storage, because object storage, like S3, is designed to scale, is relatively cheap. But the point is that there is a mismatch between the interface used by object storage and the interface of the tool that we use in our pipeline. They expect to use access data just using local files. So how to solve this problem? And here where comes this Fusion solution. Basically, essentially, is a kind of adapter that make it possible to access data over an object storage like S3 bucket or cloud storage bucket, like if it were a log file system. So when you have S3 bucket some files, you can access locally using a virtual file path, the /fusion/S3 and the bucket name. And then behind the scene, there is this driver that automatically transforms all the access to this file path to IO operation in a native manner using the API of the underlying object storage. But at the same time, also, this removes all the need to use the AWS S3 command line tool, but also optimize the usage of the API behind the scene. This is more or less how does it work. The schema or the deployment of this technology. You have Nextflow running into a compute node, they launch the job execution into another compute node, and most of the time this happens using containers. So there is your job, and within the same container, we operate this fusion driver. This is the component that creates the interface between the job I/O and the object storage. So there is not just this adaptation layer, this translation of API operation to S3 API operation, but also there is a caching system that make it possible to optimize the deployment on the data pipeline, the access to the object storage. So one important component that is done by this technology is to have an efficient caching using the local scratch that there is in the compute node in a transparent manner. But surely you may think, okay, but there are plenty of these tools that allow to mount an object storage into a local file system, S3FS, Airclone, Amazon Mount Point. There are many. What is different in Fusion? The difference is that we design to make it optimized with data pipelines, taking consideration also the data model used by Nextflow pipelines. In Nextflow, every time that you run a pipeline, each task works in its own working directory. And using this assumption, basically, we can remove a lot of limitations that there are in some file system, because basically this model guarantees there is never concurrent access to the same file into Nextflow pipelines. So relaxing this assumption, we can optimize the allocation and the access to the underlying object storage. It's designed to run to a single job, like I was showing you before, not hosting in the compute node. And also, there is a very smart algorithm behind to prefetch all the data when you need to access data from the object storage at the same time to upload in background. So using this second level cache, they change a lot the efficiency of this system. Also, something that seems trivial or minor is the ability to support symbolic link, but this is going to have a big impact on the execution Nextflow pipeline. I will show you later why. And also super easy to be deployed. There is no moving part to be installed or services to be configured. It just requires a few configuration settings to the Nextflow configuration file. So to compare, to make more evident what is the difference between this technology compared to other S3 fused driver, we compare with a benchmark with Airclone and Amazon Mount Point using FIO. This is a popular file system benchmarking tool in different scenario, reading small file, reading large file, and writing files in a sequential and random manner. This somehow simulates the access of data made by the pipeline. And you can see that when you read small file, all these technologies have more or less the same throughput. The fastest one is Airclone with nearly 9,000 megabytes per second. Mount Point came immediately after 8,000, and then there is Fusion, so a bit slower compared to this solution, and the same for random read. But, more than but, here what is interesting to see is that basically all these tools benefit by the fact that you can cache this file, this small file can be cached by operating system, caching system, essentially. So basically, when you are reading this file, you are reading from the memory of the computer, not from the remote storage. This is why they are all more or less fast enough the same manner. But when we work with large files that are much more common with genomics pipeline, life science pipeline, the number change dramatically. You can see that Fusion can read a file like this, 6,000 more or less megabytes per second, Airclone 85, and Mount Point 3 megabytes per second. So it's huge difference, and more or less also the same for random read. So why there is this big difference, and why Fusion managed to be so fast compared to other solutions? For this point I was mentioning before, because behind the scene, it operates a second-level cache, so there is not anymore the benefit of operating system cache, but still Fusion has its own caching system that make it possible to make so fast compared to other solutions. To be fair, on point, there was a bug in the version that we use for this benchmark that's been fixed recently, so it's expected to be faster. And the same, we see also the same benefit when we write over the object storage, and why Fusion is so fast, because again, Fusion works essentially with the local scratch disk and upload in background to the search. So you are not uploading directly to the object storage. Also, a benchmark comparing. Yeah. Okay. And comparing the execution real-world data pipelines with Fusion or AWS Batch using also S3 and FSX for Lustre, the shared file system provided by Amazon. So when we deploy a pipeline, that in this case was an F-core or RNA-seq, with just using S3, this pipeline require more or less 800 CPU hours to complete successfully. And using FSX is much faster because we remove all the overhead to transfer the data from the bucket to the job container to copy the result back. So it's nearly twice fast. But what is interesting that using Fusion, we can have the same performance. So the same performance using a shared file system like Lustre for FSX for Lustre. Even more interesting is the cost and impact on the cost of this technology. Here we are reporting the cost for the compute, the I/O operation, the data transfer, but also to store the data of your pipeline for 1 month. So for using Amazon Batch S3 is more or less $124 per month. The FSX is much more expensive because you need to use this separate file system only for the pipeline execution to store the data, so more or less $300. And instead using Fusion, only $69. Here it can be interesting to notice part of it is cheaper, but how is possible that it's cheaper than S3? Because we say that Fusion work on top of S3. So ideally, it should be the same. There is not much sense being it's cheaper than S3 itself. As this was puzzling us, also us at the beginning, because it was not clear what it was happening. We were thinking there were some bugs, something like this. But then we realized that this is the benefit of the ability to create symbolic link over the object storage. So since Nextflow is designed to work and to reference file using symbolic link, but when you use just S3, this is not possible, essentially create many more copies of the same data during the pipeline execution. But when we have the ability to create again symbolic link, basically we did the pipeline create much less data compared to the only S3 version of the same pipeline. And we also compared this effect across different pipelines. There is huge difference in some cases. This is an F-core RNA-seq that produces more or less 1 terabyte of data when using Fusion, 90% less data. SC RNA-seq, 32% less data. ADAX-seq, minus 44. With SARIC is a huge difference, nearly minus 61% less data compared to only when you use only S3. So this approach gives you a much better usage for the data storage when in the cloud. This technology is supported by support all the major object storage for the cloud, AWS S3, Google Storage, and Azure Blob Storage. We consider the version for S3 production ready. We are still working to optimize the version for Google Storage and Azure Blob Storage. This is also available both using Seqera platform, so our platform for deploying Nextflow pipeline, but also just using Nextflow command line 2 is enough to configure properly the configuration file to use Fusion. And then the other component which we are working a lot recently is Wave. It is a containerization service for data pipelines. And containers are key component in data pipelines that we use nowadays. Nextflow was one first tool using container in a systematic manner for data pipelines. It was also the reason why it became so popular, this technology. But the point is that in the last 10 years, changed a lot how we use container into our pipeline. The beginning, the idea was pretty simple to add just a container with all the dependencies into the container. And when we were running the pipeline, we were just using a container. Now pipelines are much more complex. They have many more tasks and jobs. And there is this pattern to use different container for each task. So you can have a pipeline with 20, 30, 40, 50 different containers, not like RNA-seq. And maintaining all these containers is not an easy task because you need to create them, upload in the registry, modify every time there is a new version of the tools, keep online, maybe using also when you use different clouds. So yeah, a lot of overhead basically in our work. So here we want to push forward different model to think the container not like a monolithic asset that is built by somebody else, but it's something that instead we can create on demand during the pipeline execution. And it's enough to know which tool we want to use into the pipeline. This system assemble the container dynamically, maybe using a package manager like Conda or Spark. And also the idea is to make it possible to optimize the container for a specific computing platform. So if you're running this on Intel, you have the container for Intel. If you're running on ARM or other system, you can have the container for that system. This is more or less schema that represent how does it work. There is Nextflow running your pipeline, launch the job, and when the job needs to be executed using container, has to wait for a container for that job, providing the information about the dependency that need to be stored into the container, the user identity, so can be authenticated private container registry, and also the platform where the container needs to run, so it can be optimized for a specific platform. And then this system assemble the container and upload into registry, so that can be used by the pipeline. I think maybe the most important point is that Wave is seen by your pipeline like a registry, but it is not hosting the container. It just delegates this to a real registry that there is behind. It's more a coordinator for the container that need to be used into your pipeline. We are operating this system since 1 year, and we have done a lot of new features in the past month, what we call container freeze, the support for singularity, the ability to scan the container for security. There is also a command line tool. And maybe the most important part are these 2 points that I was mentioning also before, the ability to create multiple architecture container, because now it's more and more common to have platform like ARM64 that essentially the CPUs that there is Mac computer also in the cloud when, with Graviton. And this provides a more cost-efficient computing capacity, but to be able to use the CPU architecture, you need to rebuild all container for that CPU architecture. That is not an easy task. So the idea instead to use a package manager that with Wave, so that basically we can rebuild all the amount of the container when you need to deploy this pipeline into this CPU architecture. And along with this, there is also the support for Spark package manager. That is a package manager similar to Conda. So basically you have a collection of tools recipe that allows you to store these components. The main difference that this package manager is able to compile the tool for not just a CPU family, but also for a specific instruction set of that computer. So there are different variants of CPU, and using this tool, basically you can optimize the compilation for a specific variation of the CPU, and then make it possible to create also the container that are optimized for a very specific CPU architecture. If you're wondering how much you can gain for this, there is this interesting research paper that is linked here that show basically the compiling the tool and the resulting container for a very specific CPU instruction set, you can get up twice the performance compared to the generic version of the same tool of that platform. And since there is a lot of stuff, I think it's easier to see in practice how does it work, this technology. I want to show a bit more concrete. I'm used here, but the command line on Wave that you can download from the Wave repository. There is a binary version for different platforms, Linux or Mac or even Windows. So it is enough to download and run it. And you have this command line that is Wave and show you what you can do with this container. And let's say that the most basic operation to just access a container with Wave, I can use -i stand for image, and then I can say Ubuntu. It is give me the name of the container to be accessed through Wave. So I have this container name that I can use with Docker, like any other container, Docker run or just pull. So doing this, there is no big benefit. It is exactly the same doing on Docker. Let's do it. So I just d equals Docker equal Ubuntu. So this is exactly the same operation. What you can see anyhow is that these containers are identical. They have exactly the same checksum independently if I download it from Wave or directly from Docker. So you may wonder why you should do this and download by Wave, because if this was a private container, it was possible to access using Wave with the credential that you have configured into Seqera platform. So basically, this mechanism allows you to authenticate container in private repository and access using the Wave service from your pipeline in different cloud without having to authenticate independently. But surely what is even more interesting is, what if you want to add some new content, your container, without having to rebuild the container? Usually, if you want to modify a container, you have to rebuild, upload, and then you can use your pipeline. But instead, what you can do here is maybe create just a script that can be my scripts into this directory. Then I create a little file that is hello.sh, where I put echo hello symposium, like this, and then I give execute permission my script. Okay, the usual workflow should be Docker build and then upload, etc. But what I can do instead is say -wave using the Ubuntu image, and then specify that I want to add a new layer into this container using --layer my script. So what is happening is that all the content of this directory will be bound to the execution of the Ubuntu container. So I have the name of this container, then I can use like any other container, Docker run, and then I can execute the script with /hello.sh. And pulling the container is running the container. I have the result. So again, here we didn't build any container, but the script was added during the pull operation and make available within the container. So what is it supposed to be better than building a container? Or here the idea is that since we were saying that in pipeline there can be tens of containers, we may need to add to all of them some script that we want to use in our pipeline, or maybe some tool that we want to use into all containers. Instead of rebuilding one by one, we have a mechanism to modify altogether all of this. That is exactly how we add the Fusion client within the container using this approach. But you can even build a container with Wave if you want. You can do just a Docker file. Like before, Ubuntu. And I want to add again the load script into user log the hello.sh, and then I want to execute on the fly. To build the container now, instead of -i, I can say -i file, and then the Docker file. And again, I need to specify this directory where I have the script that I want to add into the container. And now I have a real build. This is the name of the container. I can run on the fly. Now it takes a bit more time because here now there is the build happening behind the scene remotely. And now we have the container. Indeed, if I jump in my inbox, we find notification email that's been sent now. That's the build ID, the username, where the container is hosted, some other metadata, the image scan I was mentioning you before. So this give you some idea, something that you may need to fix from security point of view into the container, etc. So this is a way to build also the container on just in time during the pipeline execution. And but we said also we don't want to use Dockerfile to build container, but we want to have more declarative manner. So imagine that we have this conda package manager, which provide tons of tools, and we can use this in our container, just in the conda package, for example, some tools or tools 230. So this allows me to create on demand a container using exactly these tools. Docker run this guy, back tools. Version. We have container, it's downloaded. And okay, you may wonder, okay, but why I should use this mechanism back tools? Why I should use this mechanism if already exists a biocontainer image for each package that there is in Bioconda? Well, because Bioconda is just a subset of Conda. In Conda, there are many more tools, and a biocontainer only cover the packaging to Bioconda. But above all, even more importantly, because most of the time, you need more than one tool into a container image. Instead, there is Bioconda bioimages, there is just a one-to-one mapping between one tools to one container image. So instead of using this approach, you can train container with any combination of Conda packages. Tools, this is 117. So in this case, I can have a container with both of them or any other combination container. So this makes much more flexible how you can assemble a container for your pipeline. And so you can modify container on demand, you can create on demand with Dockerfile, you can create Conda packages or Spark packages. Also, before we were saying that we may need to use container for specific CPU architecture. For example, you may want to build a container not for Intel, but for ARM64. It's enough that you have this flag and you have a container with this tool for this different CPU architecture. Now, if I try to run this, I will get an error because I cannot run this container that is for ARM on this virtual machine that is for Intel. And this. So, but this shows that basically how you have a container for a different CPU architecture. And another thing that was mentioned before, this idea of the Fritz container. Fritz container is basically the fact, if you notice, every time that I run this, I have a slightly different version name for the container. If I do 3 times, I have this number that represents the identity, the checksum of the container content is always the same, but this part instead change all the time because this represents a unique token for the container request. And some users say, okay, this is nice, but I don't want the container to change the name all the time. It mess up the tracing on the pipeline execution for the container. So this is why we added this capability that is Fritz that basically consolidate the container with a stable name, uploading to a registry that you have specified, that is the repository. And for example, docker.io I use my own wave demo. And basically now we have the same container, but it does not change over time. Every time that you execute this, you get always the same container name. But in the same container, just is frozen somehow. It does not change. It's have a persistent name that stay along the execution of your pipeline. And the last thing can be interesting to see is also the support for singularity. Singularity is very popular when you run pipeline on-prem because Docker does not fit well into HPC environment, but Singularity has its own image format, is different way to create the specification file. Instead, using this system is enough that you say Singularity and basically create a container in the Singularity native image format, and that is hosted also into the Docker registry. This can be a bit confusing because usually you are used to use Singularity. You know that Singularity create a local file that represents the container file. But it's also possible to upload this file and pull this file from a container registry. This does not mean that Docker can run the container, but still we can store the container into a Docker registry and pull from there using Singularity. Singularity exec. The only difference that there is this ORAS : / prefix. And this was bad tools. And it's downloaded on fly around this container. So without having the local file, basically it's downloaded and managed by Singularity itself. So this more or less all the capability of this service. I use the wave command line, but when you want to use this with Nextflow, you don't need to use the wave command line because it's integrated into Nextflow itself. This is also, we added a new command for Nextflow, the TZ spec, that essentially allows you to see all the container used by a pipeline execution. For example, Nextflow spec, sec, and nav. And when you run this command, it shows for each task which is the container is going to be used. This is the basic version of this pipeline that use always the same container for all the tasks. But if I want to use wave for this, I just modify the Nextflow configuration file and say wave enable true. And maybe I want to use this technique that create a container using the conda information that I have associated into my pipeline task. No, wave conda by wave strategy, that is conda. And now, using again Nextflow spec, it tells me, it's 1 second, but now I have the Salmon container for RNA-seq index. I have always Salmon for this quantification step, but the multi-QC container for multi-QC step, FastQC, etc. So if it's not clear where comes this package, it comes basically from the association that I have in the pipeline code. In the module, each module has the declaration of the conda package, and the container are built on demand using this information to the pipeline module. And finally, also to show this capability, Nextflow config to use maybe Singularity for this. I need to enable the freeze capability. I want to specify the build repository, and that is docker.io, my own repository. With demo. And then also Singularity, because I want to run this pipeline with Singularity, enable true. Okay, now if I repeat again, I will get the Singularity container for this pipeline execution created with conda packages and hosted in my container repository, my container registry. Okay, this may give you an idea how is flexible, how the service, or also how is integrated into Nextflow. automatically basically will pull a use this container while running the pipeline execution. Coming back about the presentation here, this service, we are released recently version 1.0. We are operating like a service in the last year. It's nearly 100 million containers, so it's quite solid. Also, we are making available as an open source technology from this GitHub repository, so you can also use, but also you can download it on your computer, or if you want to modify or contribute the code, it is possible. Also, we are making available as an enterprise distribution for a customer that want to install this on-prem to manage the container into their infrastructure. And finally, okay, let's jump into Nextflow. This is the pillar of this technology, this ecosystem. And the last year, the main work, not surprisingly, was related to make more interoperable across all the ecosystem with Wave and Fusion. So one new thing that there is into Nextflow is the support for the Spark packages that was mentioned before. Like now we can declare the dependencies for the task, not just with Conda, but also with Spark. So Spark can be used somehow similarly to build the dependencies in the local execution or with Wave container, like I was showing you before. And also along the same manner, we added the support for different CPU architecture for the same reason. So you can specify that a task can run for Intel processor or a specific CPU target, or maybe Graviton, etc. And then again, this information is taken by Wave that create the container for this task execution. Fusion is now first-class support file system for Nextflow pipeline, as I was telling you before, can be used across CPU, cloud executor like AWS Batch, Azure Batch, Google Cloud Batch, but also Kubernetes. So this makes much simpler the deployment Nextflow pipeline using Kubernetes cluster, because remove the need to have a shared file system. Also, local executor, you can even run your pipeline locally and use a remote object storage. This makes more sense, maybe apart from testing, if you want to scale a pipeline into a single virtual machine into the cloud, without you can use the object storage with the local executor. And finally, there is also the support from SLAR, LSF, and GreenDengi batch scheduler. This makes more interesting instead for the deployment of Nextflow pipeline on-prem with the object storage storage system. And why we should do this? Because at the end, also on-prem, we have very similar problem like in the cloud. Shared file system is the bottleneck for the scalability of this data pipeline. Instead here, the idea is not used natively as trio unless we are using a Spark cluster into the cloud, but maybe to use a S3-like object storage that you can operate on-prem, like Minio or Chef, and to use as a scratch work directly for the pipeline execution. In this way, instead of using the shared file system. The benefit is this more or less the same that we have in the cloud. The object storage model provide a more efficient use of bandwidth, because it has been designed for a system which bandwidth is a scarce resource, so scale better. Also, it's much better in the handling of small files and the files metadata. And Nextflow tend to create small files, all the .command file, but also the tool, not just Nextflow. And also simplify all the automation to collect all this garbage during the life cycle of the pipeline, because you can have just some automation route to delete all this file using some tags, etc. The disadvantage is basically that you need an infrastructure that have a fast local scratch storage in the compute nodes. This come back with the idea of the schema. Does it work? Is Nextflow run the compute node? The schema is the same. The only difference is that we have an S3-like object storage that maybe can run on top of the shared file system on dedicated storage. So I think the interesting part is that we remove the bottleneck that there is in shared file system, because the job tend to use as much as possible the local storage instead of working always over the shared file system. But the access much more distributed. This should alleviate or mitigate a lot of the bottleneck into the network and the shared file system using this approach. Also, along with this, there is a new plugin for Nextflow, what we call Cloud Cache. Nextflow maintains a local database when you run it for the cache metadata. And usually it is basically run when it's distributed into a shared an HPC cluster over the shared file system. And so always, sometimes there is some problem because not all file systems match well with this local database. Instead, using this plugin, all this metadata is not stored locally, but again, is stored into the cloud, into the object storage that we use like a database, essentially. It is also another piece to try to mitigate this problem on the access of Nextflow over the shared file system. New things that have been included in the very last release Nextflow, 23.11.0, is the support for Singularity OCI mode. So we were saying before that Singularity use its own image file format, but recently they have added the capability to run natively Docker container. Now you can run Docker container, but you need to download a transform basically to a Singularity image file. This takes time, it's not efficient, create other problem with the file system. Instead, this capability automatically run a Docker container because use behind the scene some component from Docker essentially. But this isn't nice because we remove this need to have double image format for our container and make the pipeline more portable across different computing environment. And to enable this into Nextflow, you need to specify this configuration option. Another enhancement into Nextflow is what we call topic channels. And if you ever use Nextflow, I guess so, you know that there are mainly two kinds of channels, what we call value channel that contain a single value. It can be read by many tasks. And then what we call queue channel, it is a way to create a connection between a task and other task. So point-to-point communication to send the result one task to another. So the idea of topic channel is to create something that is more similar broadcasting system. You have many tasks writing over the same channel, over the same topic, and many tasks can read from there. And the main use case that originated the idea of this topic channel was this pattern that there is into NF core pipeline, in which many tasks need to send out the version of each tool, and then there is a continuous concatenation on the same channel to create an aggregation of all these versions. Instead, the idea here is now that you can create, in this example, there are only two tasks, but in any case, you can have an output, they send over this topic, this version, that you can have another task that always use the same topic, as many as you want, and then you can reference the topic channel, and this can be used any other task. So you are getting a channel that get all the data that is coming from all these tasks in a single command. Along with this, something that we are adding soon is what we call the command output type, a new type into the process definition that essentially execute a command on the fly. It can be useful to collect some metadata from the task execution context. And this again came from this pattern that is in a core pipeline. If you notice, all the tasks have this boilerplate at the bottom. So there is the real command that you want to execute, and there is always this snippet of code in all tasks. It is a bit create some noise, I think, into the definition of the task. I would like not to see this because it's not what the task is really doing. So instead of using this approach, the idea is to change and to keep the script just running the real command need to be executed. And the version of the tool that the task is capturing into this snippet instead is executed by this output definition. So basically, I'm telling the output should execute this command, and the output this command is captured then by the channel. So this make a bit cleaner the definition of this task when you need to define something like this. Roadmap for next year, what we are going to implement in the future. There are plenty of stuff. Actually, this stuff on Singularity has been already done. But I would like to focus a bit more, instead of talking one by one, on this idea of what we call DSL3, that is not going to be a new reimplementation by the language, but more a consolidation using a static type version of the language. So now there is a lot of problem that came from the fact that all the language is executed in a dynamic manner, especially when there are error messages or failing conditions. It's very difficult to capture and provide a nice feedback from what is failing. So we want to write a version Nextflow that is much more static oriented, so that there is a parser behind the scene that can capture much in a better way all the error conditions that there are in the code, the reporting in a more systematic manner, also to provide a better experience for the developer when you use an IDE, so that when you write the Nextflow code, the environment can suggest you what you can do or what you cannot do. So these are the main idea how we want to improve the language. And okay, I think you enjoy. I hope that you enjoyed this presentation and this idea above all, which we are working to grow Nextflow into an ecosystem of tools, each of them specialized into a specific problem on the deployment and scalability of data pipelines. Always continue to keep the focus on this idea to abstract away of the complexity of data pipelines, allow scientists like you to focus on the real work and the logic of the pipeline. So thank you again for your attention. Also, I take the opportunity to say thank you all the team working into this technology. Thanks a lot.
So I was wondering, how do you deal with the noisy neighbor situation with Fusion? Because obviously my S3 is not designed to go that fast. If I have multiple people like trying to access Fusion, how does it cope with that? Let's say if I've got like 20,000 samples going through a BAM modification pipeline, how do I ensure it's sort of balanced and doesn't act as in a bad way towards everybody else using the S3 system? Is there a rate limiting system?
So your main concern, I didn't get what's the main concern of the BAM file.
So my main concern is that if I have a fair number of hosts using Fusion to access S3, how do I ensure, do I have to do the rate limiting at Nextflow level, or should I do it at Fusion level? Is there some kind of way of making sure they all play nicely together?
So the way I think is just a way to simplify the installation. So it's completely indifferent from the point of view of the execution, the pipeline. And then all the point is that in any case, when you use an object storage, you need to make accessible the data that is into the object storage, into the container. There is no solution to this. The only way that we can do this is copying the data in a brute way. So AWS CP and copy into the container. Instead, what we are proposing in this approach is to have this integration layer that make this data transfer more efficient.
Yeah, I was more asking if I've got like a lot of hosts doing that all at the same time, how do I sort of shape that traffic? How do I make it be nice?
Storage like S3 has no problems on scalability. Can cope. No, maybe in on-prem is a different kind of story. Sure, you have to have, but S3 object storage can scale quite a lot.
We did kind of break it once.
If there is an Amazon representative here, we can discuss more.
Yeah, so S3 scales on prefix. So you have basically the amount of GET requests is limited by a prefix. So you have 3,500 requests per second for a prefix. So if you get into problems with parallel transfers, you should just change the way your data is partitioned in your bucket. But to get to hit those limits, you would have to try reasonably hard. Okay. So I guess following on from that, I think the core principle why Fusion has been so useful is that you delegate that sort of thing to the instance level. And so the mounting of that data into the instance happens at the instance level, which is why we need to use Wave to inject the binary into the container and then get that data in. So essentially, you are bottlenecking on the networking available for that instance to get that data in. And so that's how you can scale and parallelize the whole process, if that answers your question. With previous iterations, it wasn't quite done like that because the first version of Fusion, we were doing it at the head node level of Nextflow, and that was throttling all of the data transfer. But now, just to properly allow it to scale, we're doing it at the instance level. So essentially, wherever your task is running is the limitation.
Hi, so I have a question about HPC systems. So I work with the cluster here at Cambridge, and one of the bottlenecks I have found is the configuration, really. Because we have several partitions, there are a lot of users, and sometimes some configurations doesn't work at the time. And then if I change partition, then I need to also change the configuration. And that, as a user, has been a journey discovering exactly what I need. So I wonder if there are anything on the works regarding automated configuration, because that would be just fantastic.
Well, there is no a standard recipe also because HPC not are all the same. There are different systems. Each HPC are different kind of storage file system. But we have on the blog some tips and some guidelines how to improve the scalability. One is to try to keep a bit more under control the number of parallel jobs that Nextflow can submit. The other is, I don't know, to run Nextflow not in the head node, but as a job into the cluster. Yeah. The other one is to use as much as possible the scratch storage in the compute node. That I think, what I understand, is not a common pattern that you have here. So there are some tips, but depends case by case. So maybe we have to see more in details what kind of problem exactly you are experiencing.
Hello, sorry in advance because this might have been already asked on Slack. I didn't check. Is there any roadmap to make Wave standard when developing NF core modules? Because when you need more than one package, then you need to go to try to find, maybe build a mood container. If it's a package that's not in Bioconda, you have to do a PR to biocontainers, and this is a bit annoying. And while Wave just solves this issue.
Yes. So there is one. There is an ongoing PR in which we are trying to improve the capability on Nextflow to provide a module local configuration that should simplify a bit the way to define the configuration for a specific module into your pipeline. This is also related to containers. And the main idea, essentially, at least what we are trying to go, is to have just one definition of the dependencies for the module using Conda, for example, because it's the best way to track all the tools that you are using into your module just with a declaration, the Conda packages. And then using this information exactly to use Wave also to provide the container using that Conda packages. And the container can be both for Docker or both for Singularity, or because we build the container for both, or because now Singularity is also able to use the same container that is always the same Docker container. So this is the main idea in which we are going to forward. So better way to have a local module configuration than to use Wave to have a single container built from the packages that you declare into the module. Okay.
Thank you.
Okay.